fix it. Okay, so we're live. Okay. Hello, everyone. Welcome to another talk in our new webinar series for the Brazilian participation group of Rubin Observatory's Legacy Survey of Space and Time. This webinar is also being streamed live on YouTube. You can find a link on our website or access it on Linea's YouTube channel, Linea MCTI. So I'll hand over to Rogério so you can introduce your speaker today.
Okay, so good morning, good afternoon, wherever you are. So welcome to this new series, as Tássia was saying, of the Brazilian Participation Group in LSSP. And it's a great pleasure and honor to have Professor Bhuvnesh Jain to be the first speaker of this series. So Professor Jain, I'm going to say a few words about him. He's currently the Walter H. and Leonard C. Annenberg Professor in the Natural Sciences at the University of Pennsylvania. He's the co-director of the Penn Center for Particle Cosmology. He's also the co-director of a new initiative called the Data-Driven Discovery Initiative, something very interesting that we're just chatting about 2 minutes ago. I have to say that Professor Jain, or Bhuv, as we know him, he is one of the leading cosmologists today, experts in different areas, but especially large-scale structure, weak lensing, etc. And it's also interesting to say that there is a strong connection, Brazilian connection, with the University of Pennsylvania. I was just putting down some names that came to my mind, that Brazilians that went through the University of Pennsylvania. So I think Marcos Lima was a postdoc with Bhuv. Lucas Faga more recently was also, I think, a postdoc with Bhuv, and so was Vivian Miranda. And Pedro Bernardinelli was a postdoc at the University of Pennsylvania. And Raul Abramo, I think, also spent some time as a visiting professor at the University of Pennsylvania. And now I think something, a very interesting first time heard it happen is that they accepted some twins, Brazilian twins. I think one is working with Bhuv and the other maybe with Gary. So there's really this strong connection of the University of Pennsylvania with Brazil. So that being said, I want to again pass the word to Bhuv. Thank him for accepting the invitation. And he's going to talk about cosmic tensions and lensing measurement from the dark energy survey. Of course, he's involved in dark energy, very deeply involved in dark energy and leading. He's a leading figure in dark energy survey and LSSP. So, Bhuv, please, the floor is yours.
Thank you very much. It's a real pleasure to be giving this talk to so many friends in Brazil, as Rogério mentioned, along with Rogério himself and Luis, who I saw online. I have a number of connections to the cosmology community in Brazil. So let me get started with sharing my screen. Does that look okay?
Yes.
Great. So I'll talk about measurements of gravitational lensing from the dark energy survey. And
so we can actually, sorry to interrupt, we can see your background also, your desktop. Right? Do you mean to show us that?
Let me reshare. Is that better?
Yeah.
Great. Thank you, Tássia.
And we see your cursor.
Okay, great. Thank you very much. Right. So the outline of my talk is I'll describe how we try to measure the growth of structure, in particular via lensing with the dark energy survey. And then I'll address the question of how to extract information from all the lensing data that we get, in particular the use of machine learning methods. And the last part of my talk will be about these cosmic puzzles. So 2 slides on cosmology basics. We use the scale factor A of t to denote the separation between 2 galaxies or 2 worms shown here in any kind of an expanding universe. and the expansion rate is defined as dA dt divided by A of t. Its value today is called the Hubble constant, h naught. Generally speaking, matter, including radiation, because it self-gravitates, it slows down the expansion of the universe, and dark energy accelerates it, speeds it up. And if dark energy takes the form of vacuum energy, then eventually it wins because its density does not go down with time. So it starts to dominate over matter and radiation, and the universe enters exponential expansion, which has a constant rate of acceleration. So that appears to be the story of our universe, though there's a lot we still don't know. The math version of this is given by the Friedman equations for the expansion of the universe. The first one is an equation for h squared. On the right are the densities of matter, all matter, vacuum energy, the simplest form of dark energy, that's a hypothesis, and radiation. The second equation gives the acceleration of the scale factor, and it involves the sum of the energy density and 3 times the pressure. It has a negative sign, so it means that if for some reason this term rho plus 3p, I'm going to ignore c square terms because we'll imagine c set to 1. So if the rho plus 3p is negative, then a double dot will be positive and the universe will accelerate. So in red, I'll jump to the standard model of cosmology, which says that to explain the data, we need something like vacuum energy lambda, something like cold dark matter, and general relativity. Of these 3 ingredients, general relativity has been extensively tested. The other 2 are mostly hypotheses. To generalize from lambda, we introduce 1 free parameter, sometimes 2, called W, which is called the equation of state of dark energy. It's the ratio of its pressure to energy density, P over rho. And it's only for perfect vacuum energy that it's exactly -1. Otherwise, it can evolve with time. And one of our main goals is to test if it is evolving with time. So that was the background universe. What about structure, galaxies and large-scale structure? That's given by this equation in the early universe or on very large scales where density fluctuations are small. Delta denotes the dimensionless density fluctuation, and its second derivative at time is given by this equation, where the h squared delta comes from Poisson equation, it's the source term, and h delta dot is the friction term due to Hubble expansion. So fluctuations grew in time, dark energy slowed their growth, and what we measure today often are things on the sky. So I'll talk about lensing, which measures something called convergence kappa. So that's a measure of the projected density. And I'll describe in a little bit that what we typically measure are spatial correlations. So this is defined as kappa times kappa, but they're evaluated at 2 points that are separated by angle theta on the sky and averaged over the whole sky. So phi is averaged over. So in the end, you're left with a function of separation theta on the sky. This is often Fourier transform to get the power spectrum. All right, so we'll get to all that in a little more detail, but let's just go over the story of how data confronts theory. So a standard model of cosmology has 6 or 7 parameters. It can be more if one considers more complicated models. But the simplest model has the density of dark matter, density of known stuff, namely baryons, dark energy, and neutrinos, which we know have mass. And then the initial fluctuations have a power spectrum, which is often simplified just to its amplitude and slope, and the expansion rate h. So these are 1, 2, 3, 4, 5, 6, 7 parameters. Sometimes the neutrino density is neglected. And so measurements are compared to predictions by varying these parameters. And we use Bayesian statistics, typically MCMC, Monte Carlo Markov chain sampling of the parameter space. And we also add a bunch of nuisance parameters, they're called, but they're not really, they're very interesting things that denote astrophysics in some case, telescope optics, atmospheric distortion. So all the other things that affect the measurement. So these 6 or 7 plus 30 odd parameters means that we are using the data to infer in quite a high dimensional parameter space. We're interested in some questions. Is the standard model a good fit? What are the values of its parameters? Do they agree with other surveys? And if you have a friendly theorist next door, they will have their own theory and they'll want you to test it. So it's an interesting question. Is a more complicated model a better fit to the data, which has, various subtleties in statistics? Any questions so far? Okay. Let's talk about the dark energy survey, which I work on along with colleagues at Penn, colleagues in Brazil, and various other places. So this is the telescope on a mountain in Chile, where I spent 3 very happy nights a couple of years ago. And let me play this little animation, I think made by my colleague Gary Bernstein, where this is a picture of a galaxy cluster, one of our first images with the dark energy survey. You can see the scale in the lower right, 200 kiloparsecs. So that's about 70,000 light years. And these are, the beautiful galaxies that belong to the cluster and some background galaxies. So that cluster fits into one of the chips, 70-odd chips of our camera. So that's the full camera. That's the size of the full moon. So this is considered a major feat in imaging astronomy, that we are able to image parts of the sky that are even bigger than the moon with very high resolution. And then we repeat these images in different filters and tile the sky like this. So you can imagine that happened in one night, and then we repeat and shift over the sky, and that's the footprint of the dark energy survey. So this is the largest galaxy survey to date, with this 540 megapixel dark energy camera. It was completed a few years ago. It has images of 200 odd million galaxies, and there's a time domain survey. So along with DES, there's 2 other surveys, the Subaru HSC and the KIDS survey. And these 3 surveys are all completed roughly on the same timescale, and they have very complementary strengths. So we have a big field of view and the biggest area on the sky. Subaru HSC has the best imaging and is the deepest of the surveys, and KIDS is in between in area, it's in between in depth and comparable in area to Subaru, and it has the biggest filter coverage. So they have infrared data on a large part of their survey. So it's really nice that although we have friendly competition, it's really nice that we can cross-check each other's results and share all the advances in methodology. So these are the names of some of the Penn postdocs and students. Rogerio mentioned some of them. So today I'll show especially the work of Marco Gatti, and also Cyril Du, Shivam Pandey, Lucas Sacco, and Marco Roveri. I've also had a wonderful group of undergraduate students, and it's fun introducing them to DES every summer. And a number of other colleagues, of course, are involved in what I'm going to show. All right, let's talk about gravitational lensing. So on the left is a cartoon of what galaxies look like on the sky. They come in all kinds of shapes and sizes and patterns. If there was a big galaxy cluster, much bigger than the typical one, then it would distort these images due to the bending of light. The bending would be most extreme in the center. Notice we can't see the cluster directly. We are just inferring its presence by the distortions it produces on the right. So in reality, in a typical line of sight of the sky, this distortion is much smaller. And the coherent distortion we pursue in cosmology is actually 0.1%. So like 1,000 or 10,000 times smaller than what I've shown here. And we measure it statistically, as I said earlier. So you can imagine the shapes of two galaxies separated by that red line segment, whose angle is theta on the sky. So we take dot products of these shapes and average over the whole sky. We can also use the equations of lensing to reconstruct the projected mass distribution that's doing the lensing. So now we don't know where it is, just using the shapes, we can reconstruct it. And so for much of the talk, I will show this projected mass distribution. Before we get to it, full disclosure, this is what an actual image looks like. Very different from that cartoon. The data is real data, looks messy. And you can see extremely inhomogeneous and cosmic rays and satellite tracks. So it's a major challenge to get a shape catalog out of this data. I will not talk about that, but it's a very interesting subject. Instead, let me jump to this mass map. So this is the largest galaxy lensing mass map we have. And the red regions are overdensities, the blue regions are underdensities. I think I can go back to this mode. So you see the pointer. So these are some of the largest cosmic voids and superclusters ever found. And so this map was made using 100 million galaxies, half the data of DES. And you can see that if you look carefully, there's an asymmetry. The red regions are denser than the blue regions are underdense. That's because of the nature of gravitational collapse. And so this map has non-Gaussian information. There's been nonlinear evolution. So the 2-point functions we measure, just to give you a full overview, are the two-point functions of lensing shown here, then the cross correlation of galaxies denoted by crosses and lensing shapes here, and the autocorrelation of galaxy positions. That's called galaxy clustering. I will stick to lensing for the rest of the talk. For lensing, we split the galaxies into 4 different redshift bins shown in the bottom panel, and we do the correlations across and within bins. That's called lensing tomography. Sorry, I'm going through some of these basics quickly. I hope you will have an occasion to learn about this part of the story more if you're not already familiar, but I'll jump to the measurement. So this is a complicated plot. Let's focus on this panel, the 4-4 panel. In 2 papers led by Alex Amon and Lucas Sacco and Simon Samaroff. These measurements were presented and interpreted. So this panel shows on the x-axis is angle going from 203 to 200 arc minutes. And on the y-axis is the 2-point function of the lensing shear. You can see it goes from 10 to the -4 to 10 to the -7. So like I said, 0.1% distortions give you a 2-point function that's 0.1% squared. So 10 to the -6 is a typical level here. And the green curve is the Lambda CDM fit. And the black points with error bars are the measurements. So this represents the 4th redshift bin, the most distant galaxies, and it has one of the best measurements. The purple bands are the regions we exclude from our analysis because on small scales, nonlinearity and baryonic physics complicate the interpretation. So this is a 40 sigma measurement. If you combine all the bins and these two different 2-point functions that I won't talk about in detail, and we use it for doing our cosmological tests. You can see that by eye, Lambda CDM is a pretty good fit, but we are interested in 10% level issues, so we look at that more closely. Let me pause if there's any questions. Okay, so 2-point functions are the standard way of doing cosmology. And there's a big part of the story, which is how to model the uncertainties in these. So we have these 7 cosmological parameters, and then there's an astrophysical model, which includes galaxy bias, magnification, but also interesting things like intrinsic alignments, that galaxies that are physically nearby can affect each other's shapes, and gas physics, the feedback from supermassive black holes in galaxies and supernovae feedback redistribute matter. So we have parameters that capture all of this complicated story, and there's a number of papers in DES that describe these models. And we do 80% of the work is in testing for how these uncertainties are affecting our measurement. So I won't go into detail of these plots, but the different contours show, as we vary the analysis methodology or the choices of systematics, how the contours shift around, and they're largely robust. So it's been a big question in lensing, given that it's a subtle measurement. You know, what will be the limitations? And it's going to be posed afresh for LSST. But there is a somewhat interesting and reassuring conclusion so far. One is that astrophysical uncertainty is a greater source of uncertainty than observational and measurement errors. We didn't know this would be the case, but this is what we found. The other is that statistical uncertainties are still a larger part of our error budget. So I don't know if this will hold even for the first full year of LSST. It requires constant effort to model and mitigate the systematic uncertainties. But as of now, we are getting a 3% measurement of the amplitude, including all these uncertainties. So this is one kind of bottom line version of our plot. So on the x-axis is omega matter, on the y-axis is the amplitude of fluctuations, represented by this parameter S8, which is defined in terms of sigma 8, familiar to many of you, and the mass density itself. So one interesting thing we've learned is that the amplitude of fluctuations is not defined in a unique way. It depends on whether you're using velocities, galaxy densities, lensing to measure it. And lensing is sensitive to the absolute depths of potential wells. And so that ends up being this combination of the amplitude of density fluctuations represented by sigma 8 and the mass density itself. So in this space, the green contours show the 68 and 95% confidence level. The dashed show another version if we are slightly more aggressive in our choice of data. And either measurement can be compared to the CMB measured by the Planck satellite. This is the primordial fluctuations of the CMB temperature and polarization. And you can see the measurements are not happily sitting on top of each other. So there's an approximately 2 sigma tension with Planck. It's about 2.5 in this plot, but if you do it in Fourier space, it's less. So roughly speaking, a 2 sigma tension. This tension is also seen in the kids and Subaru surveys, as I'll show in a little bit. So I'll talk about the Hubble tension and this tension, and it raises, very intriguing questions. Most of all, how significant is it really? And so from the data side, we can ask, can we extract more information? So can we directly extract higher order correlations like 3-point functions, statistics of peaks, clusters and voids, topological statistics, or just do full field level inference, as it's called? So I'm going to talk about 3-point functions and field level inference with machine learning for the next 15 minutes. So this is a 20-year-old paper that I wrote with Masahiro Takada, who was a postdoc here, where we measured and modeled the 3-point function of the lensing shear. So let's take a minute to see what that is. So if you go beyond 2-point functions, you get new information by putting triangles on the sky and measuring the components of the shear relative to the centroid of the triangle. Because there are 2 components at every vertex, 2 times 2 times 2, you get 8 3-point functions, and 4 of them, shown in this left panel, carry cosmological information. The simplest is the tangential component. So if you imagine a point mass in the middle, you'll get tangential distortions of galaxies, and that's the black line plotted against the opening angle of a triangle. So as you vary the opening angle, you can see the 3-point function varies quite a lot and even crosses 0. So in that sense, it's very different from a 2-point function, which is like a smooth double power law. The red and blue and green are other components that I won't talk about. So this has a lot of information, but its overall signal to noise is smaller than the 2-point function. So it took us quite a while to get enough data to measure this. And I was very excited when in a paper led by Lucas Secco, we were able to measure that first 3-point function of the lensing shear from DES. So the red and blue curves show 2 different triangle sizes, and the solid and dashed are data and simulations. So you can see each pair of curves is pretty consistent. So the world out there is consistent with what we expect of lensing in n-body simulations. It's always interesting to see that in a new regime. So we've made this measurement, and we are pursuing an end-to-end analysis of this 3-point function. It's quite complicated because there's a lot of triangles when you vary their size and the other 2 parameters that define a triangle. Meanwhile, Marco Gatti fearlessly did an analysis of just the moments of the lensing mass map. So he got most of the 3-point information via the 3rd moment, and he combined it with the 2nd moment in these 2, I think, very impressive papers that describe the methodology and the measurement from DES. The red curve shows the 2-point function, the green shows the 3-point function, you can see that the size of the contours is about 3 times bigger. So it's less constraining, but they're complementary. So when you combine them, you get the gray contours in the middle. And the yellow is the Planck measurement. And so this is a 2% measurement of S8, the tightest that there is. And it's in 2.8 sigma tension with Planck. So this means that I certainly believe that weak lensing measured with galaxies has a fairly serious tension with the CMB. Before I come back to tensions, a few minutes on machine learning, because we are still leaving out close to half the information. So can machine learning extract all of it? There's been a series of papers in the last 5-7 years. And this is one of the more serious attempts from the Zurich group, where they used convolutional neural nets trained on a bunch of simulations. The simulations sample the parameter space as shown by the black dots. So they train a bunch of CNNs with lensing maps. They take the measured lensing map and they ask which parameters is it closest to, and they get the blue contours, which are half the size of the 2-point function contours. So this was from the kids survey, and it looks pretty good. There's a lot of ongoing work in how to improve machine learning, and there are some challenges that are going to take quite a long time to fully address. One of them is to figure out what features of the mass maps the machine learning is using to extract the extra information. And Marco has used analytic wavelet type transforms to understand this question. So this is work in progress that I'll show a little bit. The second question from deep learning that is ongoing is how to get reliable confidence intervals. There's been tremendous amount of work in deep learning, as you know, from ChatGPT and everything else. But getting confidence intervals is not a natural strength of deep learning, but there's a lot of progress. So for now, let me take a side route of trying to understand this non-Gaussian information better. This is a paper by Sihao Cheng et al. That shows that given a input field like this mass map, you can decompose it into a series of wavelets, and you can separate the information on different scales by looking at the reconstructed field from the wavelets. So you can see the leftmost panel has small scale information, the rightmost panel has large scale information, and the wavelets let you capture the correlations between scales as well. They can do some things quite beautifully. So this is a series of patterns in nature, ranging from turbulence to solar surface to lensing mass maps. And these wavelet-like transforms can recreate these patterns, not perfectly, as you can see here, but pretty well. So this is quite a remarkable feat from a finite number of coefficients. If you think how hard it would be for a Fourier series, for example, to reproduce such a wide range of non-Gaussian features. This is a quantitative demonstration of their appeal. So this is a covariance matrix plot from Marco showing second moments in the upper left and a bunch of other statistics based on wavelets. Let's focus on this middle panel. And you can see that compared to the real space second or third moment, the covariance matrix is pretty band diagonal. The real space moments have very strong off-diagonal covariances. So the wavelets have really, separated and controlled the scale distribution of the information. They do other things as well, namely they pull the higher order information into low order statistics because they, you do a nonlinear transformation, non-local transformation followed by some simple nonlinearity like absolute values. The bottom line is that in tests with simulated data, Marco finds that he can gain a factor of 2 in cosmological parameter constraints, and he's compared to even second plus third moment. So if you compare the blue curves to the blue colors, there's a factor of 2 shrinkage. So we're excited about this because it's, an analytic transform. It's somewhat interpretable. And it's approaching the performance of deep learning methods. So going back to just 3-point functions, we've learned that developing a reliable machinery for precision cosmology takes a really long time. So there's a number of higher order statistics that LSST and Euclid and other projects are exploring, but getting them to the point that they have all the systematics and have been validated is a major challenge. Simulations are indispensable, and to the extent that you can use analytical tools, whether it's halo model or perturbation theory, it's very valuable. And this part is something that is almost hopeless for machine learning. So that will remain a worry. And this, how to interpret and understand machine learning remains an open challenge. We have a practical challenge for machine learning methods to validate their approach using other people's simulations, not just their own. So if you're interested, feel free to contact Marco and me. But for now, let me give you the summary of where we stand with weak lensing. I showed you the DES result. Last month, the Subaru HSC survey produced some nice results. And the KIDS survey has already published their results. So the galaxy lensing surveys are shown by these contours, 2 sets of curves for DS and KIDS, solid contours for Subaru, and there's Planck. The 3 lensing surveys are entirely consistent. Each of them has a 2 sigma tension, so you can imagine that it's more significant if you combine them. By the way, if you do a test of dark energy just within the galaxy surveys, we generally find it to be consistent with lambda. So the tension that we are, scrutinizing is the discrepancy with the CMB. Any questions?
I have a question, if I may.
Mm-hmm.
It was on your slide 24 when you show the contours with the 3-point function and the 2-point function. It seemed by eye that when you combine the two, then it was agreeing with Planck. Right? If you look at sigma 8, the gray overlaps totally the yellow, right?
I think you would have to zoom in to see that, and it's better to see it in the S8 omega matter plane. Here I showed sigma 8 to show the complementarity of 2 and 3 point, but they don't agree. Yeah, they're both small, and it's a 2.8 sigma tension. Of course, to compute the tension, we have to go to the full parameter space, and use, one of these tension metrics that Marco Roveri and collaborators have developed, and we get a 2.8 sigma tension. So it's true that when you project onto some particular parameters, sometimes the contours look closer than 3 sigma appears to be. So you have to go to the full parameter space.
Okay, thanks.
All right. Let me see if I can move this. Okay, great. So let's talk about the early versus late universe. Many of you are familiar with the Hubble tension. So the expansion rate of the universe measured at close to the present time has a value that looks like this if you use supernovae calibrated with Cepheids. So it's 73, roughly speaking. And if you use the CMB, it's 67. And if you use another method of Big Bang nucleosynthesis combined with a late time calibrator like DES, you get the same thing. So the statement is that if you measure the early universe and extrapolate to the present time to predict what H0 should be, you get a value that's lower. So the universe, the direct measurements show that the universe is expanding faster. And that's really odd because we do the prediction based on Lambda CDM, and Lambda is considered kind of the limit of how fast one can make a universe expand, at least with a single component of the smooth dark energy. So this is a puzzle. The real story is a little more complicated from the data side. Some late universe measurements are closer to the CMB. This story is going to keep evolving with something like annual updates. Hopefully the James Webb will help the Cepheid and TRGB calibrations of supernova measurements and clarify the story. But for now, it does appear to be a significant tension, at least to me. I already showed you there's also a tension in the growth of structure, namely that we find lower amplitude than expected. So to understand why, we can look at this pie chart where the upper plot shows the universe today. It's mostly dark energy. And a quarter or so dark matter. The universe at the time of the CMB had a very different color scheme. It was mostly dark matter and neutrinos and photons and baryons, right? Dark energy was negligible unless it takes some unusual form. So there's a lot of room to play in principle with the properties of neutrinos or dark matter or dark energy that could change the expansion of the universe between last scattering and the present. In practice, these theoretical games are very constrained because we do have measurements over much of the cosmic history between the present and last scattering. In particular, supernovae and BAO rule out any kind of significant modification, say, of dark matter or even of dark energy. So they have to be pretty close to lambda between redshift, say 1.5 and 0. To understand the growth of structure tension a little more, there's a lot of work going on in the Brazil group of DES with harmonic space analyses of DES. This is an earlier study led by Cyril Du, where we measured the lensing two-point function in Fourier space and then did approximate way of inferring the true 3D power spectrum. And then we took the ratio with the CMB Lambda CDM. And so as a function of 3D wave number, we could identify the bins that have a lower amplitude. And this is useful because it shows you that they are not just the high K nonlinear modes, but even the quasi-linear regime of 0.1 to 0.2 shows some deficit. So continuing this exercise will be quite useful. This is the most provocative plot I know of in the literature, where not only lensing, but also redshift space distortions are combined into the red contour. This is a few years old. There isn't an updated version of this yet, and this is Planck. And so this particular plot shows a higher than 3 sigma tension. So the universe today is expanding faster and has slower growth of structure than the standard minimal model of cosmology. So I'm going to wrap up pretty soon with 2 slides. First is about theory, how to resolve it. So it could be that there's new species or new interactions in the early universe. Gravity is not described by GR. One of the most popular models is called early dark energy, where there's dark energy providing 10% of the energy density before around last scattering. It could be coupled to matter. It could be coupled to neutrinos. There's a lot of work in this. These are just a small set of references that are just, set of work that I've been involved in, but there's a lot more literature that I'm not trying to capture here. So the general consensus is that late time modifications are very difficult because of the constraints of supernova and BAO data. But there are still exceptions. There's a pretty fun couple of papers that Harry Desmond, Jeremy Sackstein, and I wrote, where we showed that if you have scalar tensor gravity, then the calibration of supernova itself could be affected in a way that lowers the tension. So it so happens that supernovae are calibrated with Cepheids, which are among the least dense objects. They are pulsating giant stars, whereas supernovae are extremely compact. So, screening theories of modified gravity can affect them differently in a way that can change the inferred H0. So the final point I want to make is that last month, the whole story of the tensions between early and late growth of structure got a new twist. And this is when the ACT collaboration produced new CMB lensing power spectra and compared them to Planck, and they were both consistent. So Planck primary, Planck lensing, ACT lensing, and SPT is roughly speaking in the same ballpark, do not show a significant S8 tension. And so now there's a possible tension between galaxy and CMB lensing, which could mean that there is some new physics at Z below 1 that galaxy lensing is much more sensitive to, or it could be that one or both of the measurements have a 5-10% issue. So this story is going to, evolve a fair bit, I think, in the next year or two, and it'll be very interesting to follow it. So let me summarize. The Lambda CDM model, roughly speaking, fits all the cosmological data sets separately, in particular CMB and galaxies. It fits them pretty well. The two puzzles are when you try to describe them all with the same choice of parameters, then we find that H0 and sigma 8 want different values in the early and late universe. Theoretical proposals are, far from satisfactory. There's no well-motivated model that reconciles all these observations. So even allowing for more complex models, there's a lot of work to be done if these tensions grow in significance. And of course, I'm not going to go over these, but there's a lot of wonderful new surveys coming online. The Euclid telescope is scheduled to be launched in July. So that's going to be hopefully everything will go well, and it'll be the first of the stage 4 surveys to start producing data, and LSST and the Simons Observatory will follow very quickly. This plot by Andrina Nicola is already, out of date. The particular dates and even the names, W1st is now called Roman. But there's a lot of fascinating data, not just in optical and CMB, but also in 21 centimeter and radio astronomy that will impact cosmology. So thank you very much.
So thank you very much, Bhuv. This was an incredible talk. I think we're really living in exciting times. So yeah, so I'm sure there are lots of questions. So let me open for questions. Any questions that people want to ask to Bhuv? Any questions, people? Rinaldo?
Hi, everybody. Professor Jain, thank you for the nice talk. I'm very impressed with all this informations for the next decade we are going to face on. But my question is about the non-Gaussian content that you have been shown. Usually, when I'd like to know a little bit more about the PDFs that are behind of the findings on non-Gaussian signatures. And usually if you go for we call a Cullen-Frey space, where we plot, for example, the kurtoses against the square of the asymmetry, we can find that the PDFs that respond to the non-Gaussian signature. So what kind of non-Gaussian PDFs are expected for the sigma 8 against, for example, the H parameter? So it's a log normal, for example. What kind of signature we are expecting to find?
Oh, that's a good question about the nature of this PDF. So a couple of points. The PDF, if you have to smooth the field to measure the PDF. So there's always some smoothing scale that's implicit or explicit. If you smooth it on large enough scales, you recover a Gaussian PDF. And its width is described by the power spectrum. If you smooth it on successively smaller scales, it becomes increasingly positively skewed. So the positive tails represent galaxy clusters and galaxies. And on the negative side, it cannot go below delta of -1, which is a density of 0. So on the negative side, the tail is truncated. So it looks like a positively skewed PDF in which the peak is shifted to the left of 0, representing the fact that most of space is underdense. So that said, saying more than that is complicated because the PDF on different scales is highly correlated. So you have to, suppose you wanted to do a PDF analysis, and Daya Anbajagane and Chiwei Chang at Chicago are actually doing that. You have to take into account the relation of different scales. So that's a nice way, alternative way to look at the non-Gaussianity. One thing that you miss when you measure the PDF is the filamentary structure of matter, for example, shows a signature of triangles or higher order correlations as you vary their shape. And so that can only be captured by actually using these particular polygons.
Okay, thank you. So in practice, it means that it's very hard to say that there is only one PDF, okay, to represent the non-Gaussianity. Probably there are
Yes.
a complex family of Gaussian deviations. So, okay, thank you.
Yes. I should add that in the quasi-linear regime, before things get extremely nonlinear, the log normal distribution represents the PDF quite well.
Fine. Okay.
And that is a useful approximation often.
Right. Thank you.
Okay. Any other questions? So I have a quick question. Tasia, please.
No, you go ahead. I can escalate it.
No, go ahead, Tasia, go ahead.
Okay. So my question is related to the part where you were talking about machine learning and deep learning. And one of the things you pointed out was the difficulty in obtaining posteriors. So this might be completely different, but I actually use machine learning for posterior estimation, and it's this method called amortized neural posterior estimation, and it gives the exact PDF. That's the byproduct in the end. So is the problem maybe related to like this particular problem, or do you think it might be able to use other methods like AMPS, for example, this amortized neural posterior estimation?
You have, some superpowers, because my first slide shows some ongoing work in which NPE stands for neural posterior estimation. So indeed, there has been some nice developments in machine learning, like Bayesian neural nets and neural posterior estimation. And so some generic machine learning methods, if you look at the different confidence regions of truth versus recovered, you get something like this. This is a big worry in machine learning, the dashed curve, that you get overconfident posteriors and you don't realize it. But as you pointed out, it takes work, but it's possible to develop methods that do better. And yeah, so I'd love to discuss further with you what you found with your experiments.
So I actually have some of the same concerns that you have regarding the models, and I mean, you can't really, since there's no physical correspondence, it's very hard, right? But I think it's useful. I think there's good work to be done if you're very careful with what you're putting in and the assumptions that you're making and everything. Yeah.
Yes, and it's definitely happening. Yeah.
Thank you.
Okay, so I have a question, because one of the big challenges, of course, is to model small scales, and this is where you're really one of the experts. And the challenges are modeling baryonic feedback, baryonic physics, nonlinear gravity, and also nonlinear galaxy bias. So but how do you think we should approach these challenges?
I mean, this is a great question and a very difficult one. So when I said that we are throwing away half the information, I really should have said half of half, because we already effectively smooth the data to suppress some of the biggest uncertainties, like feedback from supernovae and black holes redistributing matter, what's called baryonic effects, or like the intrinsic alignment of galaxies that have fallen into clusters and have had tidal interactions. So we smooth over all of that. And that's a real shame. The surveys have this information. Some of the, from the measurement side, these scales are measured beautifully. So there is a parallel effort to extract parameters of baryonic uncertainty, galaxy bias. And if you're, new to cosmology, one version of this is that there's a lot to be done and it's super challenging, and both analytical methods and machine learning can be very powerful. So far, the progress is difficult to describe in any simple way. So we have not found, this particular bias model to be super successful. We have not found this type of hydro simulation captures reality very well. And so both the quality of data and the approaches we take to summarize the small scale information need more progress. And I don't have anything more insightful to say at the moment.
Yeah, thanks, Bhuv. Yeah, I know that's a big challenge for us. Any other questions for Bhuv? Bhuv, would you mind sending the presentation so we can post in the website, or is that a problem for you? You can, if there's anything, you can take it out, and that would be great because it's a wonderful presentation. So if there are no, sorry?
I'd be happy to.
That's fantastic. So yes, Walter.
Oh yeah, I have a really quick one, so taking the time for it. So I was wondering for these, when they compute these non-Gaussian and triple correlation functions, I was wondering how the redshift uncertainty in the estimation of galaxies, or the sources at least, could affect the triangular shapes at the end. So when you compute the triangles, may you have some uncertainties due to redshift, or because it will generate not perfect triangles, maybe? So I was wondering something in that direction.
Yeah, so that's a good question. We don't actually attempt to draw triangles in 3D space. We only consider triangles on the sky, and then we forward model the redshift distributions. So we measure and we predict triangles on the sky. So to the extent that the redshift distribution we use in the prediction isn't correct, we'll make an error. And that part of the error is similar for both the 2- and 3-point function. And it's important because it translates into an error in the inferred amplitude. But as far as the shape of the triangle goes, it's not a major problem, because remember, the source galaxies on the sky are just the background. What we are modeling is the sum of the deflections all along the line of sight. And that's done using the Limber approximation. I'm sorry, I can't explain that better without a blackboard.
No, but I see. Thank you. Thank you.
So do you have a follow-up, Walter? Because you have a hand up.
No, sorry.
Okay. So, Reinaldo?
By the way, about the triangulation technique, this is a technical question, but it's very important to me to know what kind of triangulation are you applying when you do for the field of the 3-point correlation function? Is that kind of Delaunay triangulation or something else?
No, we don't actually do any tessellation. So this is like, if you imagine a map, we are literally putting down triangles on a curved sky, and measuring the product of the density on each vertex.
But is it possible to apply in a tessellation approach? For example, if I have,
when you measure the clustering of galaxies, suppose you wanted to measure the 3-point function of the galaxy density, then you could consider density estimators like Delaunay tessellations. Yes.
okay, thank you.
Okay, so I don't see any hands up. So if you can, please open your cameras and then we can all thank Bhuv for this very nice. Thank you very much, Bhuv.
Thank you. It was a pleasure. Good to see you.
It was great. So I send an email and then you can send me the file for us to put in the page of our Brazilian participation group. So thank you very much for everybody, and especially to Bhuv, and see you next time.
Thank you so
Goodbye.
much.